Today we will look into the problem solution, but today we will cover all the both open circuit test as well as short circuit test. Okay, so mm, problem solving on OC and SC test. So let us note down a problem. For a minute, I will. Right. Consider note down the problem. Uh, 4 kVA, 200 by 400 volts, single phase transformer, supplying full load current at 0.8 lagging power factor. The OC and SC test results are as follows. The results of OC and SC tests are given. So let us note down now. If people are coming late and disturbing the class very much every day. Okay, so tomorrow onwards, I want to log the meeting at 5 minutes after the start time of the class. I will log the meeting so that no one can enter. Okay, so they won't be able to disturb me anymore. So OC test. OC test is 200 volts, 0.8 amperes, and 70 watt. This is on LV side. Okay. Next, SC test. 20 volts, 10 amperes, 60 watt HV side. So these are the test results. Okay. So what is the question? Calculate efficiency secondary voltage and current into primary at the above load, right? So I hope that you have already noted down. You are noting down parallelly this problem. Now we'll go into the solution. Given data, what is given? So transformer LV side voltage rating of transformer is 200 by 400 volts. Power factor 0.8 lagging. So now the kVA is given, right? kVA is how much? kVA of transformer is equal to 4. Now the solution is, so what is the efficiency we want, right? So to calculate the efficiency of the transformer, we must know all the losses. So iron loss, is iron loss given? Anybody please respond? Problem? Anyone please respond? Are the iron loss given in the problem?
No, sir, not directly.
Huh?
Not directly.
Not directly. So I told you that in the previous class, whatever the wattmeter reading we will get in the OC test is iron loss, and whatever the wattmeter reading, power reading in the short circuit test, that is equal to copper loss of the transformer. Okay, so iron loss of the transformer is equal to how much? 70 watt. Next, copper loss of the transformer equal to 60 watt. Okay, so in order to calculate efficiency, we need all the losses, right? At the same time, we need to have the input and as well as output. So if anyone is there, whether input or output, it is sufficient since we are already having the losses. So if, right, is it clear?
Yes, sir.
So total loss, how much is the total loss?
30.
The total loss of transformer is equal to 70 plus 60, 130 watt, right? Now to find out efficiency, we need to calculate a output. Okay, output power of transformer is equal to its kVA into 1000 into power factor. Okay, you remember this formula. KVA and power factor is given that you can multiply these two to get a power output, right? So directly without, if you multiply it without 1000, if you remove this 1000, you can get a kilowatt. That's it. So this is 4 into 1000 into 0.8. So this is 3200 watt. Okay, here. Now output is there. Now we can calculate efficiency. So percentage efficiency is equal to output power divided by output power plus total loss, total multiplied by 100. So this output power is how much? 3200 divided by 3200 plus 130 watt into 100. Quickly tell me the answer. So it is 96.09 percentage, approximately 96 percentage. Okay. So is it clear to all of you?
Yes, sir.
Now,
Yes, sir.
hmm?
Yes, sir.
So 96% is the efficiency of the transformer. Now, what are the other quantities are asked that are asked to find out? Secondary voltage and current into the primary at the above load. So when the transformer is delivering a output of 3200 watt, right? What is the and 3200 watt with a power factor of 0.8? You have to find out what is that secondary voltage and it's a current that is entering into the primary. Voltage in the secondary, current in the primary. Okay. So here let us find out this. So first one is our A. Second, let us find the B. So for this, we need to calculate some. We need to find out some information from our SC test and OC test. Okay. So mm, output. What is the output here? Output of transformer is 3200 watt at a 0.8 lagging power factor. So don't worry about the lagging power factor. Power factor is nothing but cos phi. Okay, where phi is the angle between voltage and current. So you don't worry about this. So whenever there is a time, I will explain this power factor. Right? I think I have already given you a hint about what a power factor is. Uh, Anybody has any idea about what the power factor is? Hello, hello. Okay.
Powered by voltage,
Huh?
powered by voltage, power divided by voltage and current.
Power divided by voltage is power factor. I know.
P by V and I. V into I.
Okay. What does okay? What is then? What is phi? So cos phi is equal to power divided by V into I. That is correct formula. But
I is
what is
cos
this
inverse
phi?
of that.
What is phi?
Phase difference
Not formula. Phase difference between.
between the current and voltage.
Yes, very good. Phase difference between a current and a voltage uh, of the transformer. Okay. So Now from the acid test, let us calculate certain things. From acid test, we are given a VSC. VSC is how much? What is the voltage given? We got in the acid test 20 volts. Current is 10 amperes. Okay. VSC is equal to 20 volts. The short circuit voltage it is called. Okay. Okay. It is not. Next, I full load is 10 amperes. Generally, in the short circuit test, how much current we circulate? Full load current of the transformer. So AC test is generally conducted on HV side, right? So this 10 amperes is nothing but high voltage side. How much is high voltage? It's 400 is the high voltage, right? So this IFL is also can also be obtained from kVA into 1000 divided by VHV. So that is 4000 by 400, that is 10 amperes. Okay, this is full load current. And a short circuit test, we are supposed to circulate this current to find the copper loss. Okay, because this is a full load, right? Transformer, when it is carrying full load, it will deliver 10 amperes. So everyone who bought a machine wants to know the efficiency of the machine he bought at the conditions where he want to operate it. At other conditions where he is not at all going to operate, right? He is not, generally not interested to know the efficiency, right? So at these operating conditions, what is the secondary voltage? That is what the question here. Okay, let us find out that, right? Now we have this. Now then we can calculate ZO2, that is VSC by ISC or IFL. Sometimes it is also called ISC. Okay, so that this is VSC is 20 by 10. This is 2 ohms. Okay, now copper loss is equal to I2 square or IFL square. This is 2 means IF2 is a secondary side, that is high voltage side only. Okay, so I2 square into R2. Okay, equivalent resistance R02, that is equal to 10 square into, sorry, so this must be equal to the 60 watt because we have calculated already, right? So R02 is equal to 60 by I2 square. This is 60 by 10 into 10. Okay, how much is this? 0.6 ohms. Now we can calculate X02. X02 is equal to Z02 square minus R02 square root over. So this is 2 square minus 0.6 square. How much is this? Tell me. 4 minus 0.2 whole square is equal to root of the answer is 1.9. 1.9 ohms. Total reactance of the transformer referred to secondary is 1.9 ohms, right? So Z02 is what? Impedance of transformer referred to HV side. Okay. Similarly, R02, resistance of transformer. X02 is reactance of transformer referred to HV side. So we have everything that is a that belongs to HV side of the transformer, right? Now there is one formula to find out the voltage drop. Okay, so voltage drop, total voltage drop. If you know the reactance, total resistance, total reactance, and power factor, then you can find out the total voltage drop. Actually, there is a derivation for this total voltage drop of transformer. there is a derivation for this formula which now I am going to write, but it is not included in our syllabus, right? Generally, it is not required for you also. Okay, so working on a problem, if you are able to solve problem on OSC test and OSC test, that is sufficient. So that is the total voltage drop is I2 R0 to cos phi plus or minus X0 to sin phi. This gives you total voltage drop referred to since we have written 2, the secondary. Here in this case, the secondary is high voltage side, for that is 400 volts. This gives you, so the plus is for lagging power factor, minus is for leading power factor. Okay, so you will have a lagging power factor when the load is inductive load, and you will have leading power factor when the load applied on the transformer is a capacitive load, right? So let us apply and find out voltage drop. So voltage drop is equal to I2 is 10 amperes, R02 is how much, 0.6, cos phi is 0.8. So since our power factor is plus, right? That's why lagging power factor, that's why we use plus. Our power factor is lagging, so we have to use plus sign here. X0 is 1.9. Sorry, here I2 is there. Okay. Right. I did not write the formula here. So I2 is 10 into X0 is 1.9 into sin phi. How much is sin phi? Sin phi becomes 0.6. Okay. Tell me the value of this. This is how much?
16.2.
16.2 volts. Okay, so this much of voltage will be dropped. So that means on HV side, what is the actual voltage? 400 volts. Okay, so 400 volts is the voltage rating of the HV, that is 400. So when you go, when you apply a load of 10 amperes on the transformer with a power factor of 0.8, it will cause a voltage drop in the windings. Okay, that means you have a transformer secondary. So induced EMF E2 is there. This is the total voltage induced from the primary. Okay, so sorry, this the resistance and reactance of the transformer will cause a voltage drop 16.2 volts. 16.2 volts, and remaining is available to the load. Okay, so this is a 10 amperes comma 0.8 lagging load. Okay, so is it clear?
Yes, sir.
So then
It is 19.2, sir.
so
19.2.
V2 and the 18.2 16.2
19.2.
what is that 19.2?
16.2 volts అని రాశారు.
I'm not getting your voice is not clear.
Sir, in total voltage drop you written 16.2. That is 19.2.
ఇక్కడ ఆన్సర్ 16.2 కాదా? రాంగా? You got a wrong answer. Okay, 19.2.
Yes.
Once check it. I have done it on my calculator. I got 16.2.
Yeah, sir, it's 16.
It is 16.2 only I got. You check it once again. So 16.2. I kept my calculator. So voltage at above load V2 is equal to 400 minus 16.2. That is how much? 3083.8 volts. Okay. So any machine, right, as the load increases, a generator or transformer, okay, whether DC generator, AC generator, or transformer. So as the load increases, its voltage slowly comes down. Okay. So primary current, third one, that is LV side, LV. How to find it? LV current, we have KVA into 1000 divided by VLV. Okay, so the 4000 divided by VLV is 200. This is 20 amperes. Okay, is it clear? Huh? If you are having any doubt, you can ask me in this, right? If you have any doubt, please ask. I want to share you a few things about this induction motor. Induction motor is a very important machine. It's a very important. Machine for industries. For industries, very important. It's not just cannot take simply. It's very important for industries, because whatever the industry you take, right, or as a whole, if you take worldwide, total 70% of motors used in industries are three-phase induction motors. Okay. For example, if in an industry, if there are 100 motors in a big industry, so out of this 100 motors, you will have 70 three-phase induction motors. Remaining are other DC motors or any AC motors, other type of AC motors are there, right? Okay. So that is the importance of the induction motor. So if induction motor replaces 70% of motors in the industries of the whole world, right? What do you think? How important it is? Does it make any sense to you? Hello. Okay. So here, if we see classification of AC motors, classification of AC motors. you will have, okay, AC motors. So under the category AC motors, you have synchronous motors. Synchronous motors. Other side you have asynchronous motors. Okay. Here the induction motor falls in the category induction motor, asynchronous motors. Induction motor is asynchronous motor. Okay. So there are other classification, other motors are also there, like repulsion motors, uh, and uh, reluctance motor, etc., etc. Okay. So your uh, induction motor is a asynchronous motor. That means there is one speed called synchronous speed. Okay. So these synchronous motors run at synchronous speed. Synchronous speed only. They cannot run at any other speed. Absolutely constant speed motors, synchronous motors. Okay. So these motors, asynchronous motors, these motors run at speeds less than synchronous speed. Okay. So synchronous speed, ns, n suffix s, n is for speed, s for synchronous speed. Is generally given by 120 into frequency of supply by number of poles of machine. Okay. For example, you have a synchronous motor, right? If it is having a two-pole machine, say example, a synchronous motor P is equal to 2, F is equal to 50 Hz. Its speed, synchronous speed N is equal to 120 into 50 by 2. This is how much? 3000 RPM. Okay, like that. Right? So it was synchronous speed. So if it is a induction motor, it will run at a speed less than 3000 RPM. It will never reach 3000 RPM. It can never reach 3000 RPM. Okay. So, but has found a numerous number of applications in industries. That's why they have occupied 70% in all the the industries of the world, right? So that is the importance of induction motor. So three-phase induction motor particularly. And another induction motor is also there. The single-phase induction motors are also there. Okay. So quickly, I will go into the construction of a construction of induction motor. Okay, it is a motor, right? It will have obviously rotating part, right? So whenever it is a motor or generator, definitely will have rotating part. When there is a rotating part, means you will have mechanical loss, right? Just now we have completed a few minutes before the transformer, in which there are no mechanical loss, that is frictional loss and windage loss. Okay, only iron loss and copper loss are present in the transformer because there is no rotating part in the transformer. Whereas in the induction motor, it is a motor, it is having a rotating part, and obviously we employ bearings to make the motor run freely, right? Obviously, even though you employ bearings, there will be a friction existing between the rotating shaft and the bearings, because of which some of the mechanical energy developed in the motor will be lost to overcome the friction at the bearings, right? So induction motor, uh, IM IM stands for induction motor. Okay, so if you take induction motors, there are two types. First one is squirrel cage induction motor. Second one, slip ring induction motor. Okay, so the main parts we will later see classification with this. So main parts are stator, and second one is rotor. Total, if you say stator and rotor, everything of the motor is covered, right? But how the stator is, what will be there in a stator, what will be there in the rotor? So stator means it is a stationary part. Rotor is a rotating part. In the DC motor, what is the rotor? Rotor called armature. Okay, the DC motor, the rotor is called armature. In armature core, armature winding are there. Stator is a field system. Okay, if you are able to remember, bring back your memory. Clear? So stator has a distributed winding. Okay, distributed winding. This is three-phase winding. Okay, so this winding is housed in a stator core. Just I will draw the core and show you. So okay, so I'm not perfect at drawing this. Good at drawing perfect circles.
So draw a circle and hold it, sir. It will get perfect.
Huh?
Draw a circle and hold it for a second. It will get perfect.
Your voice is somewhat low. How to draw a circle?
Draw a circle and hold it, sir. You should not break the circle in between. You should complete the circle and just hold it for a second. And
Then what happens?
It will get I mean round.
In a tab, huh?
Yes, sir.
Okay. Wow, perfect. Thank you. Okay, then we'll go for this. So that is I will draw another circle. Very nice. So this is a stator, and inside of this we will have another the blue one, right? So this is the thickness of outer frame. I will shade it outer, the outer frame, This is frame. This is frame. Of stator. Okay, and the inner one is a, I will shade it with blue color. So this thickness is a, okay, I should not shade it because I have to do something with it. This is the stator frame, cylindrical one only. See, these are, if I hold it, what it will be? If I draw ellipse, then it will become a perfect ellipse. Very good. Okay, what we see as a cylinder here, that is a stator frame. Inside another cylinder is there, right? So you will have inside another cylinder, that is a stator. So inside of which inside of uh, this core, you will have slots. Okay, so whenever you take frame or any core, obviously it is a inside of this, you will have red circles I'm drawing inside of these tooth like uh, things or conductors. Three-phase distributed winding it is. Okay, so this is a stator. So everything is made up of the conductors are winding. So this is a winding, stator three-phase distributed winding, right? And this is stator core. Again, it is a laminated core. In every machine, whether AC or DC, you will have laminated core only to reduce the loss. Okay, now here we'll see. So stator three-phase, this is a construction of stator. Okay, if you take a rotor, so the rotor, it will have a shaft. 2 minutes, I will finish. Okay, so on the surface of the stator, you will have slots, grooves. Otherwise, you can think them as grooves, so that we can place conductors throughout the periphery, outer surface of the stator. You will find grooves. If you look from this side, it will look like a just like I have drawn now for DC motor, right? like a gear wheel like thing. Okay. Right. So there will be conductors again here. So conductors. This is called rotor winding. Okay. Or this is rotor winding for squirrel cage. Sorry, slip ring. Sorry. This is for the slip ring induction motor. And that will be copper bars. This is for squirrel cage. Copper bars means thick rods will be placed in a squirrel cage induction motor. Right? If it is a slip ring induction motor, you will have just like a winding, just like the winding of similar to that of a starter winding. Okay, distributed three-phase winding will be there for slip ring induction motor. That is the only difference. So based upon the type of rotor used, the motors are these induction motors are classified as uh, sorry, squirrel cage induction motor or slip ring induction motor. Okay, so this is the classification, two types of induction motors, and this is the construction. Okay, so for starter only we will give supply. So the three windings of the starter are brought outside. Three-phase AC supply or power supply. Okay, that is what. Right, you will have some more parts are there which are important from the construction point of view. Those things we will cover in the next class. Okay, so if you have